Welcome to the overview video for the antibiotic resistant organisms lesson. So within this lesson, you're going to learn some of the basic concepts of antibiotic drugs. You're going to be exposed to a handful of different examples of targets, structural targets of different antibiotic drugs, and the mechanisms of actions for targeting those exact structures. You're also going to be exposed to information about a couple of organisms that are a big public health issue because of their antibiotic resistance. So you're going to learn about Staphylococcus aureus and many of the diseases that it can cause. You're going to learn about Neisseria gonorrhoeae and gonorrhea, and then along with gonorrhea, you will learn about chlamydia because clinically they look very, very, very similar. So you kind of approach them almost as a pair. So you can, watch all the videos and get all the great information. But with this summary, there were a couple of things that I wanted to point out and kind of tie up some loose ends and emphasize. So this lesson really begins with the basic concepts of drugs, of resistance. So there are a couple of really good videos on how drug resistance occurs, and the idea of natural selection, that we're actually selecting for mutations that already exist. So how does drug resistance occur? Well, random mutations are the vast majority of resistance, and that's actually basically how all resistance begins. Is an accident happens. There is a mistake when the bacteria is being copied, and that accidental mistake caused the target for the drug to be changed, or it caused an enzyme that would normally act on one substrate to suddenly act on the drug instead, something that was accidentally advantageous to that bacteria. Many of the mutations are not advantageous. Many of them are negative, and then that cell would die. Or you'd have a mutation that doesn't really change anything. It's just neutral, and the cell is just left to survive. And that's how these drug-resistant mutations are. Most of the time, they would just be neutral, because if the drug's not in the environment, then there's no great advantage to having that mutation. But if we do put the drug in the environment of that cell that happens to be a mutant, then that will be the one that's able to survive and reproduce. And then all of a sudden, the babies, the next generation of that organism have the mutation because that's what's passed forward. So classic example of natural selection. So if you're not the cell that actually has the accidental mutation in it, how else can you get it? Well, you can acquire it. You can do classic kind of DNA exchange, acquire new DNA. Remember, we talked about using the pilus and conjugation. We talked about picking up new DNA from the environment through transformation, or viruses moving DNA from one cell to the next through transduction. So those can all be ways of getting the mutated DNA if you are not the one who has the mutation occur within you, or it wasn't, a parent cell of yours. Okay, so now I want to shift over to talking about the drugs. So before you dive into all the examples of the targets and mechanism of actions of all the different drugs, I want to pause for a moment and talk about the generic qualities of a good drug. So a good drug would be one that's healthy in your body, that doesn't get into your body and cause a toxic side effect with the chemistry within your body, or one that you can't take along with other things. That would be a perfect drug. In the real world, if you can't take it with orange juice, then don't take it with orange juice. Or if you can't take it along with this medicine, then those people just can't take it. But in a perfect drug, you would not have to worry about any kind of toxic side effects, either within your body or from external things that, foods and other drugs that you put within your body. It also would not react badly to your body, so it wouldn't have solubility issues. In other words, you could take it, for example, like orally, and it wouldn't get into your stomach acid and turn into, a little rock. And it also would be stable within your body. You would take it, you would ingest it, and it would last. It wouldn't immediately get destroyed by stomach acid. It would hang around in your body to where it could go find every little nook and cranny and kill the bacteria that it's targeting. This stability would also be on shelf life too. That would be, on if it could not expire quickly in the pharmacy, that would be a great advantage also. Another thing that you do not want your drug to have, so a perfect drug would be non-allergenic, no allergic reactions. That's really difficult to predict whether, 1% of the population is going to have an allergic reaction, but sometimes it does, and a perfect drug wouldn't have that. And speaking of difficult to predict, a perfect drug would be one that was very, very difficult and really impossible to get drug resistance by the microorganisms it's targeting. Again, perfect drug. The goal drug would not have resistance issues. It wouldn't have allergy issues. It would be stable and soluble in our body. It wouldn't cross-react with anything else. It would be cheap to produce. It would be cost-effective. That brings up medical ethics and some other things. And then it would have a great long shelf life. It wouldn't be temperature sensitive. You could put it in a backpack and a tent for 50 years and it would still be just as effective in the end. So those would be kind of the goals. Do any drugs truly match all of these characteristics? No, but that's what we're going for. That would be a gold standard. Okay, and then the kind of second half of this lesson is all about the different diseases. So a big chunk of those are going to be Staph aureus diseases. You don't need to know the nitty-gritty details of the virulence factors of Staph aureus, protein A and all of that. I've given you some examples of different exotoxins and exoenzymes for Staph aureus. Those would be what you need to know, but anything that's discussed beyond what's in the PowerPoint is more than you need to know. So some different Staph aureus diseases that you're going to be responsible for. We start with kind of the more benign skin things, the carbuncles, furuncles, impetigo. Those are surface level skin infections. Folliculitis remember itis is inflammation of. So anytime you see an itis, that means inflammation. So folliculitis is the follicles, hair follicles being inflamed. Carbuncles are another word for boil. So this is a deeper, the hair follicle pocket. There's our little hair. The pocket gets all full of bacteria causing inflammation, and that inflammation kind of puffs up, and that's what a carbuncle is. A furuncle is when this pocket gets really, really large. You might think of it as more of like an abscess. So furuncles are deeper down into the body tissue, meaning you were, from the epidermis to the dermis and maybe even down into the subcutaneous. So when you start getting down in here, you're getting closer to blood flow, which means your immune system is getting excited, getting heavier levels of inflammation, so you're starting to feel more systemic symptoms. When it's up on the surface, your immune system is not nearly as worried about it. Surface level infections are just that, surface level. So you tend to get localized symptoms and not more systemic things. The deeper it gets, the more systemic your symptoms tend to get. So carbuncles are just boils. Furuncles are abscesses bigger. You tend to get more systemic symptoms like, flu-like symptoms as it gets deeper and deeper. Speaking of surface level, impetigo. So impetigo is not just a hair follicle that, one little tiny spot. Impetigo tends to be more all over, larger sections. It tends to be around the nose and the mouth because about half of us, a little less than half of the average human population carries Staph aureus in their nasopharynx, in their nose. So your nose drips. That if you're one of those people, then that drip can have bacteria in it, and your nose gets all irritated from wiping it, and then that can start infection. And so that's really what impetigo is, and it spreads as you touch it. So it's on the surface of the skin, but it's not just one little spot. It ends up being kind of a wound, an open wound on the skin, but it's very shallow, highly contagious, but very shallow. And because it's so shallow, you just get the localized, redness, crustiness, weepiness around that area, but you don't get systemic infections, systemic symptoms because it's localized. So that would be impetigo. Most of the time our immune systems are strong enough by, puberty that we grow out of impetigo. if you had it at all as a kid. The next level of skin infection would be cellulitis. For this one, we're getting deeper. We're getting more into the deeper dermis, past the surface level stuff and getting deeper. It's a much more dangerous infection because it can turn septic. You can get down into the bloodstream. And go septic. So with cellulitis, you usually get high levels of inflammation. It starts as a wound, and then that wound gets very, very red, very warm, very inflamed. If you start having streaking coming off of your wound, that's a sign. It's called lymphangitis. That's a sign that the original infection is now moving, and that can, turn fatal. That's when you start getting into sepsis and the bacteria, this aggressive bacteria moving around the body. Okay, the next level of skin infection, not on this picture, is necrotizing fasciitis. So this is what the media would call a flesh-eating bacteria. And there are many different organisms that can cause this, Staph aureus being one of them. Actually, Streptococcus pyogenes is even more known for causing necrotizing fasciitis than Staph aureus, but it happens. So flesh-eating, these are organisms that have a large number of invasive exotoxins, exoenzymes that can, at very quick speed, go from a small wound to a huge, massive open wound because of these virulence factors that are just destroying the cells. So necrotizing fasciitis is characterized not only by cell death, but also by the cells basically becoming unglued. Think of like the exoenzyme collagenase destroys collagen. So and hyaluronidase, it destroys hyaluronic acid. So all of these little connective chemicals and connective tissues are destroyed. So the glue holding the cells together get destroyed. And so it's very, very fast progressive, can get into the blood, can go septic, and be very, very fatal because of the speed with which it progresses. Okay, other Staph aureus diseases to talk about. A handful of exotoxin-based ones. So scalded skin syndrome is a skin disease that's exotoxin-based. If your Staph aureus infection that's wherever in your body, the infection could be anywhere. It could be in your big toe. But an exotoxin named exfoliatin is produced. And when that gets into the bloodstream, the skin all over the body gets affected. And you get a peeling skin type presentation, as well as you have exotoxin in your bloodstream. So you get, fevers and a full body systemic infection. Speaking of exotoxin in the bloodstream, toxic shock syndrome. Toxic shock, again, the Staph aureus infection could be anywhere, but a certain exotoxin is produced that is a super exotoxin, causes your body to go into a shock-like presentation, just like we talked with septic shock, where the blood pressure very suddenly drops, your heart rate goes up, your respiratory rate goes up, your oxygen levels start dropping, and you go into shock. Because this is such an aggressive exotoxin, it actually puts you into this chemical storm, the cytokine storm, and puts you into shock. Toxic shock syndrome is associated with tampons. So some people say that only females can get it, but it's actually not true. Anyone who has a Staph aureus infection that produces that particular exotoxin can get this disease. It's associated with tampons because there used to be a brand of tampons that were the bacteria grew really well on. So if you happen to have those on your hand, then you got that bacteria on the tampon, which was a warm environment, the bacteria would grow. This particular tampon was really scratchy and could provide a way for the exotoxin on the tampon to get into the bloodstream and put you into shock. The other thing with that particular brand of tampon was it was supposed to be super absorbent, and you're allowed to leave it in for 24 hours, which gave plenty of time for the toxin to be produced. So now that those rules have changed, the materials with which tampons are made of are controlled more closely, and you're never supposed to leave a tampon in more than 6 hours. So you're reducing the amount of time to produce that exotoxin. Speaking of time, the last disease that Staph aureus disease that you're going to be held responsible for is actually Staph aureus food poisoning. So it's essentially the same exotoxin that if you eat it, you get really, really nasty, very violent GI response. Within usually a couple of hours from eating it, you're both diarrheaing and vomiting, just purging. can typically run a fever for a couple of days as your body is just absolutely purging this awful toxin out of your system. Um, Fortunately, in that situation, it's isolated to the GI tract, so once it's out, it's out. If it gets into the bloodstream, then it's a whole different story. Okay, so those were overviews of some of the chemical, the drug details, some of the resistance details, and a little bit of the Staph aureus disease information. You'll get a lot more information on all of those things in the lesson. As always, if you have any questions, please post to the Muddiest Points discussion board, and myself and your colleagues will help answer them. Good luck.